Hello.
Hey, good morning, everybody.
Good morning.
Welcome to the morning session of the third day of the NASA Gregory G. Leptoukh second online Giovanni workshop. This is your host, Jennifer Brennan. It is just a couple minutes before 10 a.m., but I would like to go over a few housekeeping items first, so we're going to go ahead and get started, okay? First, to ensure the best audio experience, for the rest of the speakers, there's one exception. For the first talk, nobody will be muted. So it's very important that you all mute your telephones so that we don't pick up any audio from people typing, coughing, whatever it is in the background while Michael is speaking. He is speaking to us by way of his computer microphone in Greece, so we want to be able to hear him. The rest of the conference, everyone will be in silent mode, so if you have any questions or issues, what you'll do is you'll enter them into the Q&A pod, which will be located on the lower right-hand corner of your screen. You'll see that on the next slide that I pull up in a moment, and that works like a chat. The webinar will be recorded and posted online to our NASA Earth Data YouTube channel, and also linked from the NASA Goddard disk site after the workshop. Speaker presentation files will be available for download not only at the end of each talk, but what I've also done today for the final online day of the workshop is I have posted all of the speaker presentations beginning from day one in a file sharing pod at the very end of today's session this afternoon, okay? So they will be there. But even if you miss that part, you'll still be able to download them later when this is posted, okay? So no worries. The program layout is as follows. Each talk will be 1 hour long. 30 minutes are allocated to the presentation with a 15-minute question and answer period that will follow each talk. And then what we'll do is we'll transition to a 15-minute break that follows the question and answer period. Again, questions will not be answered using the raising hand function. It has been disabled. We will take all questions using the Q&A pod at the end of each talk. What I'd like to do next is actually turn it over to the workshop organizer, Dr. James Acker, who is a senior support scientist at the Goddard Earth Sciences Data and Information Services Center, or the NASA guest disk. What he will do is he will go over today's agenda. It is my pleasure to introduce our workshop organizer, Dr. James Acker. Jim?
Hello, can you hear me?
Hello, good morning,
Yes,
James.
we can hear you.
Hi. Yes, today we're going to have 4 talks, and the first talk will be given by Michael Taylor, who is currently in Greece, and he'll be talking about how to train neural networks to look at global aerosol particle size distributions. And followed by that, we will have Siobhan Roy from England, and he is going to be looking at phytoplankton dynamics and time varying indicators. Following that, and a nice 2-hour lunch break, we'll come back and we'll hear from Yang Xu, and he is talking about the radiative forcing of carbonaceous aerosols over California. And finally, your host will give a talk looking at the precursor and late conditions when a bloom of phytoplankton caused the city of Toledo to have to rely on bottled water for a couple of days. So we have a nice varied program today, and I'm looking forward to Michael's talk because he's using a lot of different NASA data sets. And so that's all I have for today, and I'll turn it back to Jennifer. Thank you.
Okay, thank you, Jim. So let's go ahead and begin today's morning session. Okay, let me pull up Dr. Taylor's bio slide here. It is my pleasure to introduce our first speaker for this morning's session, Dr. Michael Taylor, who is a research fellow at the National Observatory of Athens in Greece. Dr. Taylor?
Thank you, Jennifer. Thank you as well for the kind introduction. Nice to be here with all of you. So today I'm going to talk briefly about the model we've been developing here at the National Observatory of Athens, whose aim is to try to recover size distributions of aerosols on a global level by a synergy of GOCART, MODIS, and AERONET data provided by Giovanni. So a brief outline of my talk today is I'm going to spend a minute or two talking about the rationale for this work, which is essentially to train neural networks to invert satellite measurements in order to retrieve daily aerosol size distributions and some associated microphysics across the globe at a resolution of 1 by 1 degrees longitude latitude. I'm going to present some results of a prototype neural network we developed to perform this inversion for a specific type of aerosol, which is dust in the Sahara in northern Africa. And then I will explain a little bit how you can go from this to a global model of aerosols by following a couple of simple steps. One is which involves cluster analysis of GOCART data. The second step involves training a neural network for different types of aerosol mixtures or compositions, or regions if you like, spread out across the globe. And the third step, which is still in an experimental phase, is performing multimodal analysis of the size distributions which are obtained with this global model. And I'll say very few words about that. And finally, I'll close with a case study of the Karthala volcanic eruption on the Comoros Islands back in 2007 as an example of how this approach can be put into practice. Okay, just before I started, this was quite an ambitious project for a single computer, single PC with 16 gigabytes of RAM, and essentially data came from 3 sources. We downloaded the full AERONET data record of inversion products for some 160 different aerosol optical and microphysical parameters. We obtained from Giovanni 3 and satellite data from the MODIS instrument on board Aqua, and the OMI instrument on board the satellite Aura, for a number of satellite measurements, mostly concerned with aerosol optical depth and precipitable water vapor. And we also made a lot of use of data provided from the GOCART global chemical model, which is available from Giovanni 4. So we made great use of Giovanni in this project. And of course, all of this wouldn't have been possible if the data wasn't made open and provided in this way by NASA GES-DISC, and in particular by the pioneering efforts of Greg Leptoukh and his co-workers, like Jim Acker, for example, who have made great efforts to advance data interfacing, accessibility, and visualization. Okay, so the rationale for this project. There is if we look at the change in climate forcing over the last 120 odd years, from 1880 through to 2003, this graph is based on that data, the uncertainty associated with the change in climate forcing due to global greenhouse gases, GHGs, which is this big red, red bar, the second red bar. I'm just looking for a pointer. Hold on a second. Here we are. These are the total global greenhouse gases. The uncertainty associated with those is about 0.4 watts per meter squared. And if you compare this with the uncertainty associated with aerosols, it's higher. They're around 0.7 watts per square meter over this time scale. So there is a need to reduce this uncertainty. Reducing this uncertainty requires a better characterization of aerosols. The characterization of aerosols is essentially, it depends essentially on the size of the aerosol particles, their volume, concentration, their shape, the composition. By that I mean the mixture of different types of aerosols, and also their source regions. I would like to point out here especially, when you look at the emissions due to different types of aerosols coming from natural or anthropogenic sources, the greatest emission sources are from sea spray and from mineral dust, which by several orders of magnitude compared to, for example, anthropogenic sources. So these are dominant emissions, and at the moment we don't have a very good understanding of their microphysics in these regions. So in particular, the size and volume of aerosols, the best source of information concerning this is, at the moment, the most reliable and accurate source is from AERONET. And in particular, the AERONET algorithm, which inverts solar radiation measurements, is capable of producing the aerosol volume size distribution, which I'm abbreviating here and in the following slides as the AVSD. And essentially, the size distribution spans a range of aerosol particle radii from 0.05 microns down here through to 15 microns. The way the algorithm works is it provides 22 values for the volume concentration at different radii. The curve here is just the black curve is an interpolation through those points, and then what the algorithm does is it finds the local minimum between these two peaks. This peak here is the fine mode, so it has a characteristic radius associated with small or fine particles, and this peak here is the coarse mode, which has a characteristic radius associated with larger particles. We'll see what they are in a few slides. And what the algorithm does is it finds the local minimum between these two peaks, performs an integral over these radii, and this integral gives you the volume concentration of fine particles, and the integration in this region gives you the volume concentration of coarse particles, using these formulae down here. I don't want to dwell on the mathematics, and if people want more information, I'd like to refer them to a couple of papers which you can see in these blue boxes on these various slides. Okay, so this is the AERONET method. One of the challenges, of course, is that while the AERONET stations which have the CMEL sun photometers, and coupled with this algorithm for inverting the solar radiation measurements, are very high accuracy, their distribution is patchy. It's also very low over these important emission regions associated with oceans and the deserts. So, for example, during a wildfire outbreak in Greece in the summer of 2007, where you can see the smoke plumes here, data to do with the microphysics, the size and volume concentrations of aerosols, could only be provided from AERONET at two locations, one in Thessaloniki and one on the island of Crete. So the spatial representativity available from AERONET is, for this particular case, was very low. It's very patchy in industrialized areas, like in mega cities. The density of AERONET sites is quite high. Over the oceans and over the deserts, the density is quite low. So this need, if you like, created an idea. The idea born of this need was that maybe we should develop a model to invert satellite measurements to provide these AERONET parameters for the optical and microphysical properties of aerosols. In particular, we did a scan through available satellite measurements, and the satellite records which were most full in terms of data which could be co-located and made synchronous with AERONET data for the purposes of producing a model involved these parameters, this list here. Parameters associated with water vapor, aerosol optical depth, and the absorption aerosol optical depth. To perform the inversion between these satellite inputs and these target AERONET outputs, which included the size distribution, the real and imaginary part of the complex refractive index, the single scattering albedo, and the asymmetry factor, we coded a grid of neural networks. The satellite data, I'd just like to repeat, was all drawn from Giovanni 3, and the AERONET data, of course, is from AERONET. Okay, so our prototype model We had to focus on one particular type of aerosol initially. We thought it would be good to focus on one type because the optical and microphysical properties of especially a pure aerosol type are better understood than more complex mixtures. So we decided to choose desert dust as a candidate, a pure aerosol type, and naturally our eyes were drawn to where the peak of desert dust is found, and that's in northern Africa. The graph at the top right is actually a segment of the mean aerosol optical depth due to dust over this region. So these two maps, left and right, actually they're coincident. And then in this region, what we then did was select a number of AERONET sites which were available in this region on the peak of the dust AOD signal. And then for each of those sites, with reference to GOCART, the GOCART data, which provides the contribution due to sulfates to the optical depth, the contribution due to organic carbon and black carbon and sea salt and dust in terms of the absorption, in terms of the aerosol optical depth, excuse me. With reference to this data, we were able to identify which sites had the highest component of dust, where dust was representative in terms of aerosol at each of those sites. So we managed to limit the collection of AERONET sites down to 7. 6 of the sites were put to one side to train the neural network, and a separate site, Dakar, was kept to one side for testing purposes. And for the whole collection, the percentage of dust, as reported by the GOCART model, was greater than 85%. So in terms of the aerosol size distributions, if you like, or the aerosol properties at each of these sites, averaged over the whole record at each of those sites, is very high. So we were quite sure we had data which was going to be representative of dust. Okay, the neural network model, it was important that we, for these sites, that we obtained co-located data between satellite inputs and AERONET as the outputs. And if I just run through this schematic very quickly, so the inputs were from the satellites. We had precipitable water, we had 3 AOD measurements, and we had absorption AOD measurements from OMI initially in our initial trials. Later on we dropped that, and the target outputs were the size distribution, complex refractive index, the spectral complex refractive index, I should say, because it is at 4 different wavelengths. The spectral single scattering albedo, again at the same 4 wavelengths, which are 470 nanometers, 675 nanometers, 870 nanometers, and 1020 nanometers, and the asymmetry factor. So then the question was, well, how do we choose the network architecture? And network architectures are determined essentially by a couple of simple parameters. One of them is the number of hidden nonlinear neurons used to perform the transform between inputs and outputs. We used hyperbolic tangent functions. And so one issue is how many of these neurons you have in your network. The second issue is what proportion of the training data you use, excuse me, let me say that again. What proportion of the available data you use to train the network, and what proportion you keep to one side to validate it. And the validation is performed with reference to a backpropagation algorithm. We use the Levenberg-Marquardt algorithm. And then what we did was we decided to create a grid of such networks where we varied the number of hidden neurons, and we varied the proportion of the data used for training. And this is shown in this graph at the top right. Each of these points represents the mean squared error between the outputs produced by the network and the target outputs which were available from AERONET, and each point is the result of calculating the mean squared error between these two things for each network architecture. Then we used a very simple criteria, which was that, well, the network that gave us the lowest mean squared error, we would choose as the optimum network. And then, having chosen the optimum network, which for this particular type of aerosol, for this particular data, we found to require 22 hidden neurons and to use 90% of the available data. We then fed the network with new data that it hadn't seen, which was the satellite inputs at Dakar, which were then processed through the network and produced the AERONET target outputs, which we then compared with the outputs provided by the network to validate it. Let's move forward. So in terms of this simulation, we had available 181 daily averages, and I will focus on the size distribution. We also calculated the single scattering albedo and the complex refractive index and the asymmetry factor simultaneously. However, they were not retrieved very well. What was retrieved excellently was the daily aerosol volume size distribution. The left-hand plot at the top here shows the data record from AERONET at Dakar, which was not provided to the network, but it was used to validate the network's simulated outputs, which are visible here on the right. The plots underneath are just the contour plots of these two things. So you can see a signal here and here associated with the coarse mode, which is what you would expect for desert dust. In terms of individual days, here are 12 plots showing the size distribution from AERONET in grey, overlaid with the size distribution retrieved from the satellite data using the neural network in blue. In terms of statistics, for each day we calculated the correlation coefficient of the AERONET distribution against the distribution obtained by the network, and what you would really want in an ideal world is a row of ones here, so that the network perfectly recovers the AERONET data. In reality, you get a range of values, and in particular, when the aerosol optical depth is low, below 0.4, there's a lot of variability here in the results. The network performs poorly here. It's possibly due to the fact that the actual AERONET retrieval itself is also not so reliable at low aerosol loads. At higher loads, the performance of the network seems better. So the conclusion of this prototype study was that it is possible to train a neural network to invert satellite measurements and produce size distributions on the daily time scale. They are good, they're not perfect, and essentially this network is capable of performing this inversion for one type of aerosol, which is Saharan desert dust. So how do we go from this to producing a global model? Well, the aerosol optical depth for different types of aerosol provided by the GOCART global chemical model we decided to use this to perform a cluster analysis. Why is this? Because, for example, I've lost my pointer. It's green on a greeny background. Just a second. So we took the GOCART data record over 7 years from 2000 to 2006 inclusive, and for example, for black carbon, the mean map is this. This is the mean of the black carbon aerosol optical depth. This is the mean of the organic carbon aerosol optical depth from GOCART over that period. This is the sum of these, what I call BB, biomass burning, which is a big assumption, but I'll come back to that a little bit later. This is the sulfate signal, and this is the mean of the dust aerosol optical depth, and this is the mean of the sea salt. So you can see a very strong band here in the southern oceans. The dust peak is where you would expect it would be. So how can you use this information to perform cluster analysis and to partition the globe into different aerosol mixtures or types. Well, what you do is you need to create a single matrix where your rows are latitude and longitudes for each pixel in these maps. The GOCART, I should say that GOCART provides data in pixels of 2.5 degrees longitude by 2 degrees latitude. We just did a simple downscaling to 1 by 1 so that we could use this information on the same scale as that provided by MODIS. There's a bigger assumption in doing that, but you'll see that I don't think the error introduced there is so critical when other things are considered. I'll come back to that point. So the rows are the longitude and latitude positions, and each column is the value in each pixel for each of these different aerosol types. So essentially each map here is 3D. You've got a lat, you've got a lat, you've got long, and you've got an amplitude, and you can convert these into one single two-dimensional matrix in this way. Okay, in terms of the cluster analysis, excuse me, we traditionally with cluster analysis you choose a number of clusters based on some insight, maybe 5 or 10 or something like this, and then you use an algorithm like the k-means algorithm to find the centers of these clusters for your data set. We decided to try and refine that a little bit to remove this subjectivity by sequentially adding clusters one at a time. So you start off with one cluster, and essentially you've got one. Imagine having one cluster with whose center is at the center of the map, so at the center of the Earth, and the values of this cluster correspond to the mean of each of the columns. So you'd have a mean percentage dust, a mean percentage sulfate, a mean percentage sea salt, and a mean percentage biomass burning. If you then go to 2 clusters, you would have 2 centers, and for each cluster you would have a different mean value of dust, sulfate, sea salt, and biomass burning, and so on and so on. You keep adding a cluster, and you see that the total distance between the cluster centers and all the data in the map decreases. It sort of reaches an asymptote. It's decreasing quite rapidly in the beginning, and then it falls off quite smoothly. Here you need to introduce a cutoff condition, and we adopted the same cutoff condition that was used in a study by Ali Omar of AERONET data, where he performed cluster analysis back in 2005 of AERONET data, and his criteria was that, okay, when the cluster centers don't change by more than 10%, we will accept that as the optimal number of clusters. And doing this, we found that the GOCART data, the mean global GOCART data, can be clustered into 10 different clusters. Once you have these 10 clusters, in each pixel, what you then do is for each cluster, you go and find to which pixels does it correspond. You extract all that data, and you find the average biomass burning optical depth, the average sulfate optical depth, the average dust optical depth, and the average sea salt optical depth. And if you put this information over the 10 clusters into a bar chart, stacked bar chart, you get a result like this, where in cluster 1, which has over 1,000 members, spans over 1,000 pixels, is around 35% black biomass burning. Due to the aerosol mixture contains about 35% biomass burning products like black carbon and organic carbon in this definition. Another 20-odd% due to sulfates. By sulfates we include not only urban sources of sulfate but also volcanic. Then another 20-odd% due to dust, and another so many percent due to marine. So you get an aerosol composition for this cluster, and you do this for each cluster, and you can see visually that there's a cluster here which is very dominant in yellow, which means a lot of dust. There's a cluster here which is quite dominant in black, which means a lot of biomass burning. There's a cluster here with a large proportion of sea salt, and the rest is more or less sulfate, a little bit of dust, a little bit of biomass burning, and so on and so on. Then you can produce global maps. How do you do this? Well, we had to choose a color scheme. So we had 4 different aerosol types: biomass burning, sulfate, dust, and sea salt. We decided to choose primary colors that can be mixed. So for our choice of primary colors, we chose red, yellow, and blue, of course, and then we added black for biomass burning, because this allows you to mix these colors in a visually useful way. So, for example, if you see purple in this plot, right? Purple is a combination of blue and red in the typical sort of pigment mixture of colors. So you can see with your eye that this cluster associated with which is purple in color has around 50% sea salt and around 50% sulfate. You can see a cluster down here, which is cluster number 9, which is dominated by blue. It's very dark blue, which means it's nearly 100% sea salt. There's a component in there of sulfate, which is why it's not totally dark blue. It's a little bit purplish. You can see the dust region here. You can see a little bit of dust with red, which is sulfate, which is this orange here. So you have a dusty sulfate band around the outside here, and you have strong dust regions here. There's another dusty source here in Australia, another one down here in the Atacama, and another one here on the west coast of America. So this gave us a visual way of seeing how aerosol mixtures are distributed globally. Having done that, we then extracted in each of these clusters the AERONET sites which were available. So, for example, this is cluster 4. The little black points in here are AERONET sites. There are actually AERONET sites having an occupancy of 32 pixels on the global grid at a scale of 1 by 1, which accounted for some 25,000 data records. Having extracted this AERONET data, which we hoped would be associated with dusty aerosol, we then co-located it with the available satellite record from MODIS and OMI, and trained a neural network following the prototype that we presented a little bit earlier for Saharan dust. But now the source of data includes a much greater number of AERONET sites, and hopefully is more representative. The plot at the bottom, the grey size distribution is the size distribution you get by averaging all the AERONET records, and the red plot overlaying it is the size distribution simulated by the neural network trained over this region. So you can see that the main features are recovered. The fine mode radius is in the right place. The coarse mode radius is more or less in the right place. There's a small difference in the volumes, but this is to be expected because AERONET is located in specific pixels, and the satellite data is available over a more diverse region. Doing this for biomass burning, which is the 5th cluster, which we call sulfurous smoke because it's mostly smoke. In other words, a mixture of black and organic carbon with a component of sulfur in there. And you can see that these regions are where you would expect them to be, over the Amazon, over the biomass burning regions of Africa, Indonesia, and northwest Australia. And these are the results. This is the AERONET size distribution in grey, the size distribution produced by the neural network trained on data from these regions is in red. So the initial results seem quite promising. A little bit of an aside here. We decided to develop a technique for taking the size distribution and seeing if it's possible to fit it with more than 2 modes, because the method developed by AERONET is excellent, and divides the volume concentration into fine particles and coarse particles, but it forces the size distribution to be distributed into those two components. However, we noticed by looking at various data sets that it was possible to see data, for example, especially from dust aerosol sources, where the fine mode was in some cases quenched. It wasn't available, and in these cases, by forcing the AERONET algorithm to reproduce a fine mode creates an error, because if you imagine trying to fit here, it means you change the fit in the coarse region. So you essentially under or overrepresent the coarse mode if you ignore the fine mode. So we developed an algorithm to take the distribution and fit it with Gaussians, up to 8 different modes, and then to extract the radii and the volume of each of those modes in the hope that this could provide more information at the local pixel level for daily size distribution. So I'm not going to dwell on it. It's a method that's recently been published, and refer people to here for some more information. It's possible that we can incorporate this as a plug-in to our model as a post-processing, and it would be wonderful if AERONET would like to trial this as well. So, okay, this brings me to a case study. These are composite maps produced from GOCART over a period of 12 days, from the 12th to the 23rd of January in 2007. They're global maps, and I would like to focus your attention on this region here. There's a little point here, which is the volcanic eruption in the Comores of the Carthala volcano. And in these maps, these are composite maps where the GOCART maps from, due to biomass burning aerosol is in green, sulfate is white, from dust is orange, and sea salt is blue. It's a bit different to the colour scheme we've adopted, which is based on primary colours. However, this was the initial inspiration for doing the cluster analysis, because these maps are visually very impressive, but what's missing is they do not provide a route to obtain the size and volume information, which is why we developed this model. So focusing on this region, on the 12th of January, you see a little white dot where the eruption begins. This dot increases in size, so you can see a lot of sulfur being emitted here from this volcanic source, and spreads out over quite a vast spatial region by the end of the period, covering the whole of South Africa. Okay, so we then decided to try and model this. We had our cluster analysis, so we knew that in different pixels over the region, each of these is a 1 by 1 degree pixel, we had a different neural network. So then we took the satellite inputs over this region, and we found that on the daily scale they were very patchy. You can see these white patches here, which are still visible even when you take 4-day averages of the data. On the daily scale it's much worse, which is why we took 4 daily averages. These are the inputs. These are inputs from MODIS for the precipitable water on average over 4 days, and these are as an example over the region. This is the optical depth averaged over these 4 days. And if you feed this data into the neural network, whereby each pixel is associated with a different neural network, depending on whether it was in cluster X or cluster Y. And then the outputs of these neural networks give you size distributions, averaged over 4 days, of course. And then from those size distributions, we calculated the volume of fine particles and the volume of coarse particles. And these maps here, the second row are the volumes of fine particles, and the third row of images here are the volume of coarse particles over 4-day intervals. Okay, so the GOCART images from GEOS5, the composite maps are here. You see the spatial dispersion of sulfate here, and there's a source of fine particles here produced by our model. Because the color scales are a little bit different, you can't notice very clearly that this is actually extending in size and extending in size. So there is some initial indication that as a first guess, this model seems to be helpful. So just to sum up, sorry, I'm going over my time, so I'm going to sum up very quickly. The prototype model for Saharan dust shows that it's possible to train a network to perform this inversion of satellite measurements onto daily retrievals of size distributions. It's then possible to produce a global aerosol model for reproducing size distributions at a 1 by 1 degree resolution. And our initial results from the case study of the volcanic eruption shows that perhaps it's possible to run such a model in quasi-real time on a 4-day timescale to obtain this information. I would like to thank the scientist in charge of this project, Dr. Stelios Kazantzis, and co-workers at the National Observatory of Athens, and Donis Gikas at the Barcelona Supercomputer Center, who helped substantially in the provision in extracting and organizing the data that I used for training the networks I developed, and the various PIs at AERONET and at Giovanni 3 and 4 for maintaining and providing the data. And last but not least, to Jennifer and Jim from ADNET Systems Inc. for kindly organizing this workshop. So sorry I ran over my time. I look forward to hearing everyone's comments and questions.
Okay. Thank you, Michael. So what we will do now is we will move to the 15-minute question and answer period. And then directly following the Q&A, we actually have a short break before our second speaker for this morning's session. Okay, so we do actually have one question, Michael, to start off, and that is it possible to add or derive aerosol, individual or clusters, time duration at different atmospheric layers in between source and sink with respect to time? If you need me to read that one again, I can.
Yes, please.
So it's a little bit long, I know. Is it possible to add or derive aerosol, and then in parentheses, individual or clusters, time duration at different atmospheric layers in between source and sink with respect to time?
Yes, okay. Very good question. Yes, what we're doing here is in each pixel, you can imagine that what does GOCART produce? In each pixel, it gives you the aerosol optical depth averaged over the whole vertical column as an output from its global chemical model. So if you can imagine in each pixel being able, for example, from LiDAR, averaging the aerosol optical depth in different layers, so for example from 0 to 1 kilometer, 1 to 3, 3 to 5, 5 and above kilometers, you can imagine performing the same analysis for different vertical, let's say, levels of the atmosphere. This of course means that you would then have to perform cluster analysis in an extra dimension, because you're also including vertical information. But I don't see a problem with doing this. You would only need to categorize the vertical layers into some standard and then perform this analysis for each layer. So yes, I think you can do it in principle. I hope that answers the person's
Thank you,
question.
Dr. Taylor. If there are any questions for our speaker, you're welcome, sir. If there are any questions for our speaker, if you could go ahead and type those into the Q&A pod on the right-hand side, that would be great. And then just as a note, the file for his presentation is listed down below in the file sharing pod. And what will happen is if you highlight that file with your cursor, you will have an opportunity to download the file. So not only is it listed here, but at the end of today's afternoon session, all speaker presentation files are also uploaded there for the entire workshop. Okay, any questions for Dr. Taylor? And here's a comment by Dr. Acker. Michael, it says,
Yes.
Calypso provides vertical aerosol data. We don't have that in Giovanni, though, because it is along orbit profiles.
Yes, yes. Yeah, one issue is the global extent of Calypso information. Yeah, I think that in the future we're going to see a move towards three-dimensional aerosol climatologies from lidar, and I do hope that the global coverage of Calypso data, or maybe from networks like AERONET, for example, uh, will make this possible. At the moment, it's limited to local domains or regional studies, but I don't see a reason why we can't perform analyses over specific regions, especially where they're substantially affected by aerosol sources, as the previous questioner mentioned.
Okay, thank you for your response. Any further or additional questions for Dr. Taylor here? We do have 3 minutes remaining in our question and answer period. If there are questions after the fact, just one note, the speaker's email information is listed on his slide, so certainly there's an opportunity to follow up offline if need be. Okay? Oh, you're welcome.
Yes, thank you very much, everybody.
Okay. Okay, so Jim said, I think we should consider the color mixing map option. It is useful for ocean optics, land cover as well. May correspond with you. Did you write it, or is it from an analysis package?
The color mixing. I did it myself. I essentially just wanted to choose a couple of colors that I could mix together, and with my eye I could recognize as something dominated by dust or sulfate or sea salt. And primary colors allow you to mix colors in terms of percentages. It was very easy to code in MATLAB by just combining percentages.
Okay, thank you. Jim said thank you. And,
it's a pleasure. My pleasure.
Thank you for your talk. Okay. I'll give it just another couple, seconds or so here. If there are not any further questions, we will move directly to the 15-minute break, at which point we will resume this meeting at 11 a.m. Eastern Standard Time for our second morning session speaker. All right, any further questions? It does not look like it. So why don't we go ahead and move to the break.